I'm struggling.
All right. I forgot to add this into your notes. I want to finish off related rates by talking about related rates involving trig. I know it's been showing up in your homework, but I just haven't had a chance to go over it until now. And then we'll use the second half to go over L'Hopital's rule and indeterminate form. Sorry, it's I did not put that in the packet, so let me give you a. Realized after the packet was made that I got to do this subject.
Thank you.
So everybody pick up this page, this handout.
How would you look at it?
All right, so with these related rates problems, we're still going to be starting off with some equation before we find the derivative, but these are all going to be, we're starting with some trig equation, and from the trig equation, we'll build the derivative from there. So let's read this example here. Fish is being reeled in at a rate of 1 foot per second from a point 15 feet above water. At what rate is the angle between the line and the water changing? So that's how you know that there's going to be trig involved if the problem ever asks you for the rate of change or involving the rate of change of the angle measure. But it's always going to be involving a right triangle. Okay, so we're with these trig related related rates problems, it's always going to be a right triangle involved. So I'm going to draw another triangle here just so we kind of just focus on the portion that we care about here. So we have a triangle that is formed from the line. And as the fish is getting pulled in, we can see that there's an angle associated with that. So I'm just going to say theta, 15, and z. Okay. All right, let's gather some information here. The fish is being reeled in at a rate of 1 foot per second. So we know that is going to be how fast z is changing. So, but is there an adjustment we have to make with that one? We know it's going to be dz dt. Any adjustment with that dz dt? What's happening to this line here? Right, it's getting shorter, right? So that we want that to be a -1 feet per second. 15 feet above water, that's part of the constants in this problem. At what rate is the angle changing? So what are we looking for? Yeah, d theta dt. When there is a total of 25 feet of line out. So that is a moment in time. Z is 25. Now, we don't want to insert that z equals 25 too early. We want to build it with a variable and then find the derivative. And in the end, that 25 is going to come into play for us. Okay, so we know we got to involve theta. We want to create a trig equation that relates the information that's provided. So which trig equation can I use that's going to hit all three? Sine. Okay, so let's build that here. So sine of theta is equal to 15 over z, right? Sine is opposite over hypotenuse. All right, I want to find the derivative. I know d theta dt will show up, dz dt will show up, but I would prefer not to go through a quotient rule here. So I'm going to bring that z up to the top before I do anything derivative. Okay, so let's find the derivative. Remember, time is still the independent variable here. All right, so sine becomes what?
Cosine d of theta.
d theta dt. Power rule here, negative 15 z to the negative 2 times what?
Easy.
Yeah, dc dt.
It would have been the same thing going through quotient rule.
Yeah, same with quotient rule, but I think it's a little bit faster, right? We just went through power rule. Okay, so let's see, cosine theta. Let me clean some of these terms up on the right side. Okay, let's see what we have here. We're trying to solve for d theta dt. We have that variable sitting here. We have z that we can put in, which is 25. We have dz dt that we can also see. Okay, so now the only thing that is left to figure out is this cosine theta. And I want us to make sure that we don't care about theta. We want the entire cosine theta to be replaced. We're looking for some trig ratio. All right. So in order to find a replacement for cosine theta, I'm going to have us draw another triangle. And this time we're going to fill out as much as we can for this moment in time of this triangle. So off to the side here, draw a second triangle. Oops, sorry. And as much information as I can. Okay, I know this 15 is set in stone. Now, this moment in time, z is what? 5. And I should be able to figure out this missing length here. Pythagorean theorem, what's this length going to be? 20, right? It's a variation of a 3, 4, 5 right triangle. So based off of this, what can I say cosine of theta is equal to at this moment in time? Adjacent over hypotenuse, we can reduce to be 4 over 5. So now this is going to replace that cosine theta. Okay? And now we should have everything that we need. We have our ratio. We're looking for d theta dt. We have the z. We have the dz dt. So here's my substitution. Cosine theta gets replaced with 4/5. D theta dt stays. Z gets replaced with 25. So z squared is 25 squared. And dz dt is -1. All right, I want to solve for d theta dt. So I'm going to divide the 4/5 over. Dividing by 4/5, same thing as multiplying by 4ths. And then we just try to clean this up here. And you will get to use your calculator on Monday's quiz. Let's do some cleanup here. It ends up to be 3 over 100. Now we always have to figure out the units of measure between our two units, right? So theta is always radians, okay? Always radians, never degrees. So we're hardly ever going to use degrees within our course. So radians, and then the time component is seconds. So radians per second. Right. Any questions here? So I think the biggest adjustment we have to make with trig related rates is understanding that you're not going to figure out what theta is. You're going to figure out the entire trig ratio, whether it's tangent theta, sine theta, secant theta, but you're also going to have to draw a second triangle to fill out as much of the size as you can, so you can figure out the ratio that can replace that trig function. So that's the unique thing about these types of problems. Okay, now number 2 has a bunch of variations here. A and B are ones that we've seen before, and then part C is the trig portion. So let's see if we can kind of put it all together. So part A involves Pythagorean theorem. Part B, area of a triangle, which has a bit of a product rule component. And then part C is where we're trying to find rate of change of that theta. Okay, so start with part A, see how much you can build, and I'll go through each part with you as well. Okay, let me know if you have any questions about part A. Hopefully you find part A's process as just review and pretty straightforward. Part B, rate of change of the area of a triangle. Okay. Yeah, gotta use product rule, yeah. Both X and Y are changing. 1/2 base times height. So because of the fact that X and Y are being multiplied, we have to go through product rule. They're both variables. Yeah.
When we know what the variable, how do we know when to plug it in and then when to use product? Like, or when to plug one in?
Yeah, so yeah, I think you have to kind of visualize the problem and convince yourself, is a side changing or not? If a side is set in stone, but the other side is changing, then I could get away with doing, like, for instance, let's say the X was the same and then Y was changing.
But
Because they're both changing, that forces me into product rule. Otherwise, if it was like 1/2 times 10 times Y, I could just do 1/2 10 times dy dt.
So the one that isn't changing is the one with the black.
That's right. The one that is not changing, you can just go ahead. If you know that value is never going to change for the entirety of the problem, there's no need to hold on to a variable. You can put a number in for that value or that side or left. Just be aware with the units involved with part B. DADT, we're talking about area over time. Area is a 2-dimensional unit, so that's why it's square feet. Time is seconds, so square feet per second. The only time you're not going to have a 1-dimensional unit if it's area or volume. Anything else is going to be just a 1-dimensional unit. So area, you got to do squared. Volume, you'll do cubed. But everything else is just, yeah. Okay. Any questions with part B?
If X over dt is -5, right?
Oh, let me see. That's right, -5, because it's moving to the right, but we don't care about direction. It's the fact that that base is getting smaller. So yeah, negative. But y is getting longer. So we expect dy dt to be positive, and we did get that as a confirmation that at the end we did get a positive value because y is increasing. Right, so dc/dt is asking is the ladder, right? So as the ladder is dropping, it is not changing its length. It's staying 25 the whole way through. So because it doesn't change the length at any point in time, we can say that's dc/0.
You figure out Trig to use it to sign up.
Good, yeah, so I think that's a good question. Because you have everything available to you, you can use tangent, you can use sine, you can use cosine, any of, sometimes you're forced into a situation where you got to do a trig function. But in this case, you have everything you need. Any trig will work. I decided to use sine because sine's derivative is cosine. It just feels the easiest derivative. But yeah, you could do cosine, you could do tangent. Oh, okay, yeah. So another reason why we do want to either just use tangent or use cosine or sine is because if you can take advantage of a constant, it makes things easier. That means you can avoid quotient rule. I mean, you could do x and y and do tangent, but anytime, huh? You can because you have all this information. You can do tangent and get away with quotient rule, but it's just a lot more work. So yeah, so I think the rule of thumb is I like to stick with sine and cosine, but also I also want to look to see what values are given to me or what size or what information I have. But if I have more than one option, then choose the option that can include the constants. That way you can just do power rule instead of quotient rule. Okay, but yeah, good question. I did not address that. Yeah, so for this one, sine and cosine will be the easiest path. But I chose sine. Yes, yeah, as long as it's exact value, fraction or decimals are fine. Yeah. And same with AP exam as well. If it's exact value, then they will accept either fractional or decimal answers. Okay, so sine of theta equals y over 50. I want to do power rule, but it just feels a little bit cleaner if I can push that 1 over 50 out in front as a coefficient. Sine becomes cosine theta d theta dt. 1/50th stays, y becomes dy dt. Dy dt, I can pull that from part B. Cosine theta, I'm going to redraw my triangle and fill out the side length at that moment in time. Figure out the trig ratio there. And then that should leave me with the variable that I'm looking for being the remaining unknown. So solving for d theta dt. And then your d theta, your theta is always going to be radians. Okay, radians per time theta. Yeah.
Cosine, would you get the answer?
You should get the same answer. Different, yeah, different answers. Yeah, if you did cosine, you should get the same answer as well. Okay, read number 3, see if you can figure out which trig equation you're going to use, find the derivative, and see if you can gather the information provided, assign those values to the correct variable, and then solve for the missing variable that they're asking for. Okay, try number 3. Okay, so based off of number 3, what's the variable that they're asking for? Yeah, dx dt, yeah. So in this case, you are involving d theta dt, but that's going to be a known value, right? We're looking for dx dt. Okay, and then which trig function did you use to build your equation? Sine, yeah. You're kind of forced into sine because that's, you have limited choice there. Four is the same-ish, so let's skip number 4, try number 5. And then we'll end with 5. Because yeah, 6 is the same too. We'll just, yeah, we'll do one more after this. So go to number 5, see if you can draw the picture. And the hint for number 5 is that it's going to be a different trig function than sine. So if you're done with 3, go to the next page, try number 5. Yeah, the nice thing about trig related rates is that it's got to be a right triangle. So you know it's got to be involving a right triangle somehow. Okay, so for number 5, recognize that the y is the variable here. the 30, that distance is not changing. Right, so we can leave that as a 30, right? That's just a constant. So which trig function can we use there? Not tangent, yeah, we have opposite and adjacent given to us, right? So we can get away with power rule, right? But what if that 30 was also a variable? Then we got to go through quotient rule, right? But here we can avoid. Sometimes you can't avoid quotient rule, but in this case, because if you have any of the sides being a constant, then you can always avoid quotient rule. Okay, so tangent theta equals y over 30. Same thing as tangent of theta equals 1/30th times y. Tangent's derivative is secant squared theta, d theta dt. 1 over 30th y becomes 1 over 30th dy dt. A half dy dt. I'm solving for d theta dt. And what I want to make a substitution for is I want to substitute secant of theta. So to figure out what secant of theta is, you go ahead and you draw a different triangle, but this time with all the sides filled in for that specific moment in time. Secant of theta is hypotenuse over adjacent. So 50 over 30, which is 5/3. I put 5/3 in for secant theta, make sure I square it. And then now it's just a matter of trying to solve for d theta dt.
Except there's never going to be a non-right triangle, right?
Exactly, it's always a right triangle. Yeah, always a right triangle.
Doesn't make no sense.
Okay, let me go through L'Hopital's rule quickly. It's easy concept, but it's very useful. This is page 27. Okay, we're going all the way back to limits. But is a bit of a shortcut involving limits. We didn't do this before because we did limits before derivatives, but now we're going to use derivatives to help us with our limit process. So when evaluating limits, what's always the first thing that we do, regardless, as long as it's approaching a real number, we always do what? Yeah, we always do direct substitution, right? That is always the first step, even if we have something called L'Hopital's rule. We never want to skip that first step. That first step is going to be key in terms of helping you decide what is going on there. So in this case, if I get a real number, then that's my limit. There's nothing that needs to be done to it. I'm only going to be having to do an additional step if I realize that there's an issue here, if there is an indeterminate form. So for instance, let's try example 2 here, number 1 here. Okay, so if I do direct substitution here, I get 4 minus 14 plus 10 over 2 minus 2. What do we get? 0 over 0. So the previous method that we would go through, which is perfectly fine, is you would look for a common factor that's causing that hole. You remove that hole, you reevaluate, and you get -3. Okay, because your direct substitution told you some important information about what's happening that there's a hole, but the limit still does exist. Now, the shortcut is that if you get a 0 over 0, you have another option available to you. And that other option is called L'Hopital's rule, where you simply take, but you can only do this if you get 0 over 0 or infinity over infinity, but typically 0 over 0 is the more useful form. If you see infinity over infinity, typically we have a easier, well, the previous methods is going to be a little faster. It's only going to be really efficient for us for the problems that involve 0 over 0. So L'Hopital's rule says I can take the derivative of the numerator and the derivative of the denominator. That will create a different version of the expression for me to reevaluate the limit, and that hopefully will take me to a real number. Okay. So what's the derivative of x squared minus 7x?
2x minus 7.
2x minus 7. What's the derivative of x minus 2?
1.
1. Okay, now this is a different version of the expression of the starting problem, but it will still produce the correct limit. Now I can do direct substitution again, and what do I get?
Negative.
Just like how we arrived at the previous method. Okay, so here's what L'Hopital's rule says. If you're getting a 0 over 0 or infinity, but typically, again, it's more useful for us if we see 0 over 0. We can take the derivative of the numerator and denominator and then reevaluate. Now, I don't want us to fall into a trap and think that, oh, I can now start doing this for my derivative. If it's asking for the derivative, I still got to go through quotient rule, right? But it's because it's under the context of a limit. Numerator, denominator, I can evaluate it separately because this will take me to the limit. But we never want to do this if I'm asking for a derivative of a function where there's numerator, denominator. I still got to go through quotient rule for that. So I can't just do L'Hopital's rule in place of quotient rule, if that makes sense. Okay, so let's try example 2. Okay, first things first, direct substitution. I get 2 minus 2 is 0. I get 24 minus 24 plus 2 minus 2. Okay. So L'Hopital's rule is really useful when we don't have algebraic methods to clean up and find that hole. Right? So, and also that's going to be our preference too. If we ever see 0 over 0, typically our first option is, hey, can we just do L'Hopital's rule? Because usually that's faster. Okay, numerator derivative is 1. Denominator derivative. Reevaluate. I get a real number. So once you get a real number, you can stop because that's your limit. Now, what if I went through L'Hopital's rule and I still got a 0 over 0? I can find, look and go through L'Hopital's rule again, I guess, in the sense, second derivative, right? But just be careful that you don't want to keep doing L'Hopital's rule until you get to the constant. That's not going to work out. Your 0 over 0 is only gives you the green light to do L'Hopital's rule once, okay? And the next thing you want to reevaluate. And if it gives you another 0 over 0, that gives you green light to do L'Hopital's rule a second time. So don't just, I see some students, they keep finding the derivative over and over again till they're down to the constant and they think that's the answer. So just make sure that you're going through the proper procedure. Okay.
Direct substitution, L'Hopital's rule, but if you get 0 over 0, what do you do?
If you get 0 over 0, you can do L'Hopital's rule a second time. If you get a 0 over 0 again after direct substitution.
Yeah, you can keep doing that till you get a constant.
Yes, but making sure that you always do direct substitution each time you do L'Hopital's rule.
Oh. Also, like, for finding the second derivative, do direct substitution.
Exactly, right. Always do direct substitution as immediately after you do L'Hopital's rule, because the direct substitution may lead you to a number answer already. We don't want to keep going further if that limit is right there for us.
Would it be wrong though?
Hmm?
Would it be wrong? If you just kept doing it, plugging it in.
Yeah, most of the time it's going to be wrong,
Okay.
right? But it's possible that that could be the way for certain problems. Okay, example 3. Okay, first things first, 0 in for x, we get 0/0. That gives us the green light to do L'Hopital's rule. What's the derivative of sine of 6x?
6 cosine 6x.
Yeah. Cosine of u times u prime. Okay, reevaluate. Cosine of 0 is 1. 1 times 6 is 6. Okay, example 4, plug in 0. Indeterminate form gives me the green light to do L'Hopital's rule once. Now, what happens if I do direct substitution after L'Hopital's rule? Okay, so that tells me I can do it again. I can do L'Hopital's rule again because I'm still getting indeterminate form. Sine's derivative is cosine. 2x's derivative is 2. Reevaluate, I get 1/2. Now I have my real number. Now I can stop. I just want to show you that infinity, you can do L'Hopital's rule, but it's just typically is not as efficient. We typically find that there are easier ways, that our previous methods of finding limits is usually faster. So here, okay, I'll go through L'Hopital's rule. So if I plug in infinity, I do get infinity over infinity, which is also indeterminate form. That also gives me the green light to do L'Hopital's rule. Again, I get infinity over infinity. I can keep going.
This is comparative growth.
Yeah, so that's how I do it. If I can see that relationship, comparative growth rates tells me it's going to be 0, but you can also do L'Hopital's
What if it
rule.
was negative? It wouldn't be compared.
That's right. Yeah, that's right. Exactly. If it's negative infinity, I'm kind of forced into. But if it's negative infinity, you're not going to get. Yeah, if it's negative infinity.
What's, for, can you just remind me like the trick for remembering?
Oh, right. For comparative growth rates. Okay, so yeah, if it's negative infinity, we have to, we can plug in, but I don't think it ends up being 0/0. But yeah, but typically it's going to be positive infinity. Let's see, this one, I'll get 4e to the 2x, and now I'm getting 4 over infinity, and that's clearly going to be 0. But compared to the growth rates is faster if you can see that relationship, that if your denominator is growing at a faster rate than your numerator, then slower over faster will just get closer towards 0. Okay, you guys have a little bit of homework from 4.4. I'm gonna post the problems, the solutions on the website later today. But we'll have a quiz review that we can go over tomorrow. Friday, new set of notes, and then Monday quiz. All right, come get your phones.
Yes.
There's just. Yeah, that's right. Yeah.
Your ski. Yeah. That's the. I feel like that's it just and all the teams have a.
Yeah, let me show you. Yesterday.
Yeah, like if you say like, right here.
Once you get that,
Like the web balance. Or like the hands up. It's just half the kind of easy as the hands of the shape.
Oh. I'm looking at 15.
this one, I gotta, take that plug both sides to get the next one down. And then I'm gonna force that into a fraction to see if I can get that 0 to show up.
So it's kind of all about making those fractions variables.
I'll go over this tomorrow. Okay.
That's different. Yeah. It was.
So.
So if we win an election, do you think it's a good idea to like reach out to the middle schools for tutoring hours?
I think, well, I think our initial goal is we wanna serve the student.
I know, but like last year, I only got one.
Yeah, I know, and I think that's part of the challenge is how can we find that connection between students and those who actually need tutoring? Because, another issue is that sometimes students who need tutoring are not proactive.
Like finding it.
And then so even if they set up with tutors, they're not the ones, they would prefer not to even do it, and so it's like pulling teeth, right? Trying to find students to work on. So, but I would say first priority is those students. And if we get into a situation, a stall where we just can't find students, then we can look elsewhere. But we're gonna try to see if we can figure out this solution first.
Just all of them, they're all there.
You got it, library. What is that?
I don't know.
Really good.
Have a great day, guys.